This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. We are starting. So I left this page down for you. You will now see people coming up and down to grab it. Okay, so what to do with this one? This is a reminder for you, but I do expect you to remember it by heart. Okay, do you remember it already by heart? It's not hard. There is logic behind. Okay, everything that there is logic behind, you can remember by heart. Okay. So what do I mean by this comment? I just want to be a little bit clear because normally in this subject, I don't care about where we position a coordinate system. These are kind of free-floating coordinate systems. What do I mean by this coordinate system having some origin of interest? It is because these x, y, z coordinates, I just want to specify from which point they are measured, from which point, okay? So this is from point G, the center of mass, okay? So you can imagine, just imagine some coordinate system, xg, yg, zg. You can stick it into the center of mass of the rigid body. Okay, why? Because then you will be looking at vectors going from G to all the points P on the rigid body. Okay? And this vector GP, yeah, RGP in frame G, that is along the green axis. Remember what it is? This is the coordinates RxG, RYG, RZG. All right, so these are the coordinates. That's why, just for convenience, we look at the projections onto the green axis. Now, if you have some rigid body, yeah, so let's say this is point G. It's a very big one. So let's say you want to calculate the inertia tensor of this rigid body. Sorry? M for Mama, who is now watching my daughter. Melody, who is my daughter. Okay, so body M, okay, about point G, and let's say you want to figure it out along the axis of some frame G, and remember, this could be somewhere else, okay, some xg, yg, zg. I don't care about where this is positioned. I just want you to realize that we are measuring the vectors RGP from this point. So what you will do is kind of copy in your mind for convenience this coordinate system G. Okay, it can just translate anywhere you like. Okay, don't be too confused about the origin of this frame G. Okay, so this copying is fine. just so that you remember that this vector RGP is starting from point G, and its components in G are in these directions, okay? So these are the components you are using for your integration in all of these integrals, all right? So for a different frame, you will have just a rotated coordinate system, okay? So what you will need to do if it's a different coordinate system you want to calculate for, so it will just be a different one. Let's say this will be F. Now both of them XF, YF, ZF, G and F are attached to the rigid body M. Okay, so if you wanted to calculate I for this body M about the same point G in frame F, you would just have a different, you would have different components for this vector. So you would be using RGP in frame F as something else. So let's say RXF, RYF, RZF. Yeah, so you will get a different inertia tensor here. It will be different from this because you are using different axes. You are measuring your projections on different axes. Okay, and again, you will kind of imagine a copy of this frame. Okay, so that would be F. That's good. Okay. So I just copied it so that it is easy for you to visualize the projections of the vector GP. So for a given point P, RGP, it will be easier for you to visualize the projections of this vector onto the coordinate system of interest to you. Okay, now, so you're going to choose every time some coordinate system and in this lecture, and then calculate this matrix for your choice. Okay, so I'm going to do a few examples, and I'm not going to calculate all of them for each example. I'm just going to pick some representatives for us to get the idea overall. And because we are a bit short in time, I'm not going to carry out any of the integrations. I trust you to be able to carry out a triple integral, and please do it just so that you revise some calculus and know how to do it. And ask me if you forgot it altogether. Ask me in consultations, all right? So now this is, I would say, lecture 1 in a series of 3 about inertia tensors. So this one is calculating from definition. Then we will have a lecture about the parallel axis theorem, or parallel axis, because we are doing in 3D. And this will allow us to shift. So if we found this about some point, say G, it will allow us to shift our calculation for inertia about a different point, okay, without recalculating all the integrals. So this is another, oh, sorry, I'm not showing here anything. So never mind. Essentially, the parallel axis theorem if we want to calculate about a different point. Okay? And then we'll have principal axis, and this will allow, so by that time you will learn how to rotate, let's say, an inertia tensor from one frame to another. All right? And also find a special frame where this inertia tensor is diagonal. You will see it's not always diagonal. Okay, so in here we are seeing these 4 examples. 3 of them we will calculate purely by definition, and the fourth one will use superposition as well. Okay. So in your lab work in assignment 2 as well, you will see that you might be utilizing these properties. So in anything which I'm not asking you to use the definition from scratch. I mean, if you have your material, use the already calculated inertia tensors. Okay, by all means, use them. And in the exam, if I need you to use a specific one, I will just supply it to you. Okay, I don't expect you to use to memorize any tables of inertia tensors. Okay, I do expect you to memorize the definition. And in case I want you to calculate from scratch, this will be the exercise. All right. So the first shape or geometry we are using is a cuboid. So for this one, what we are calculating in this slide is Ixx. Okay, I won't say the G in short. So Ixx is on this top left corner. Okay, and so the actual formula is this one. Now frame G, the green frame G, sorry, here it's red. I chose myself in a convenient manner. So in a convenient manner, these axes are normal to the faces of this cuboid. Okay, why? You will see that it will make the inertia tensor diagonal. So how to actually carry out the integral? Okay, maybe if you have a look, the XX component, the integrand itself, the inside, is ry squared plus rz squared, which is what I have. And the rho, just because in this example I'm assuming, this is kind of given, uniform density, I can take rho outside of the integral. So this is rho, okay? And all I need to do is set the limits correctly to cover the entire volume. Okay, because I'm working with Cartesian coordinates here, it will be simple, just kind of breaking down this cuboid to small cuboids and kind of going along the z first and then along the y and then along the x, okay, covering the entire volume. You need to use your calculus understanding to pick a strategy how to integrate over the volume, right? So I mentioned in the last lecture, be careful, all these limits are going here from negative, say, c by 2 to positive c by 2. You can't do it from 0 to c because of what I just said. Your vector, your coordinates here are measured from point G, okay, which is in the center. So in the center, the maximal, say, RZG, the maximal you need is c by 2, and the minimal you need is negative c by 2, not 0 and c. Okay, so be careful. And where did this m come from? This rho, I can isolate it from this equation of the mass of the entire cuboid, and then present the result for this inertia, moment of inertia here. I can present the result using the mass of the body rather than using its density. Okay, so I strongly encourage you to carry out the integration and make sure you get the right answer, okay, at home. And then the next example is IXY. XY is this one in the middle top or the middle left. Okay, so for IXY, the formula is Rxg, Ryg multiplied. All right? Now, you can see here, at the end it becomes 0. Okay, the limits of the integration are the same. So this is easy. Once you figured them out, it's the same for all of these components of the inertia tensor. And why is it 0? First, you will be integrating according to z. Okay, so I think it would still be fine. And then the next thing would be, say, integration by according to y. Then you'll get something with ry squared by 2. You substitute the limits, and you'll get a cancellation. And essentially, you will get this kind of 0 every time when you will have some kind of symmetry. Not only, but definitely when you have some symmetry. How does this symmetry thing work? I will mention it again later, but in this case, if you have a symmetry plane, let's say Zx. If Zx is a symmetry plane, okay, that is, I can cut this shape along this plane. I can cut it, and what's on the two sides is the same, is completely mirrored. If it's completely mirrored, there is this symmetry. Now, the axis that is normal to that plane of symmetry, in this case y is normal to that plane of symmetry. Y would be such that any inertia product containing y, like xy or zy, that would become 0. So Ixy, Izy would become 0. And because here all of these axes are normal to a symmetry plane, all of the products, inertia products, would become 0 in this shape, okay, by this choice of axis. If you choose frame G to be a bit in a different way, okay, a bit tilted, then your, say, xg, zg will not be a mirror, and then you won't get zeros outside the diagonal of the inertia tensor. Okay, if you haven't followed, that's all right. I'll repeat that again later. So I also encourage you to carry out this integration and get the 0 and figure out why it is 0. All right. Any questions so far? Yeah.
Would you always be on the center of mass, or?
What we are doing in this lecture is calculating the inertia tensor about the center of mass. So this is the title of the lecture even. Inertia tensor about the center of mass. And I'm utilizing the basic definition. Okay? And my answer is no. Later on, you'll learn how to do it about different points and how to transition between points. All right? But in this lecture, we are only interested to calculate I, the inertia tensor about the center of mass in this lecture. All right? Why? Because it will appear in the formula h dot equals sum of moments, where h dot, or h, the angular momentum would depend on I. H is I omega, as I was showing you. Now, this formula, h dot equals sum of moments, is applicable for the center of mass. So we would need to get the I about the center of mass. All right, so it's important. Any other questions? All right, now this is the total result. So we just calculated this 0 here and this 0. Remember, it's symmetric. And we calculated the first component, so m by 12 times the sum. And if you are doing all of it, you can already infer from the xx, how the yy and zz inertia, moments of inertia would look like. Okay, so if you want, you can use this result. Given any cuboid, you can use this result. Just make sure you understand the directions. So for instance, if you need the xx component, then you would need the b and c dimensions, which are normal to where x is pointing. Okay? So just for you to understand so if you're given another cuboid with other dimensions, be careful how you interpret this result onto your cuboid with your dimensions. Okay? Okay, next shape is the cylinder. And what we will do here is a transformation of coordinates. For our ease of integration, instead of working with Cartesian coordinates, x, y, z, we would be better off working with r, theta, and z. Right? Are you familiar with cylindrical coordinates? Okay, so for this transition, we would need to define, for the sake of integration, to integrate correctly, we need to use the Jacobian or the determinant of the Jacobian of this transformation. Okay, so that's why I have here this piece of volume, dv. If I'm using Cartesian coordinates, it would be drx, dry, drz. Okay, so a little cube. And if I'm using this r, theta, h coordinates along the, well, if I'm using this cylindrical coordinates, the piece of volume is not just dr, d theta, dh. It has this r as well. Okay, so this r here is the Jacobian of the transformation. Do you know how to get it? So if you have your transformation here, yeah, you would need to construct the Jacobian matrix, which would be that I'll call this x, y, z. So dx, dr, dx, d theta, dx, d h, and then dy, dr, dy, d theta, dy, dh, dz, dr, dz, d theta, dz, dh. Put them in a matrix and calculate the determinant of that matrix. If you do that, you should get r. Okay, things should cancel with the sines and cosines. Okay. Try to verify that you are getting your Jacobian r, and then you know what to place here. Or if you want to look at it more geometrically, you can look at a piece of volume. In this case, now I'm a terrible drawer, so. Sorry. Yeah, so this is the axis of the cylinder. This will be your dH, dr, and d theta. So this length here, because this is r, this length is r d theta. So this little volume is r dr d theta dh. Okay, so notice how the units are kind of meter cubed. Okay? Does it make sense, guys? Okay, so you can either think of it geometrically or more algebraically with this Jacobian matrix that I was mentioning. This J, you need the determinant of that. So the determinant of this matrix, drx dr, drx d theta, drx dh, dry dr, dry d theta, dry dh, drz dr, dry d theta, sorry, z, drz dh. Okay, and this you will get r. Okay, where these are the formulas for the transformation. Okay, this is a convenient choice for the transformation to work with r, h, and theta. All right. So I also want you to notice how my choice of z here is along the axis of the cylinder. Okay, so this cylinder is axisymmetrical about z. This cylinder is axisymmetrical about z. And by the way, if you have an axis like that, axisymmetry axis, so it means that there would be no inertia products involving z. That is, izx or izy would definitely be 0 if even if it's not a cylinder, but as long as there is a cylindrical symmetry about this axis z. Okay, so even if it's a kind of bottle, maybe for that bottle there would be some products of inertia, but not with the z, not izx, izy. Now my choice of x and y directions, this is important. My choice of x and y is pretty arbitrary, right? You can see that. So let's say if this is the cylinder, I could, if this is z, my x and y could be like this, or like this, or like this, right? All of these options, I'm going to get the same result for ixx and iyy. I'm going to get the same result. Okay? And they are also equal to one another. So because it doesn't matter, this is a nice trick. Even if these axes are rotating relatively to the cylinder, it will still be the same ixx, iyy along the rotated axis. But in this lecture, in general, we are assuming that the red axis frame G is attached to the rigid body. Remember, it's attached to the rigid body. So if you have, say, a rigid body and frame 3 is attached to that rigid body, all right, then you are essentially calculating your inertia in that frame 3, if it is a convenient one. All right, so we are working with body-attached frames here. Okay, they rotate with the rigid body. An exception for that, if you have a cylindrical symmetry and rotation of axis about this axis of symmetry, you can still use the results for this coordinate system and this body, even though they are not completely attached. There is relative motion. Am I clear? It was a bit weird explanation. Maybe I'll draw it when we finish. So for this cylinder, if you calculate I xx, what I would, so this is the definition. You can look at the handout. Ixx, again, by definition, ry squared plus rz squared times rho. Okay, so for this one, I would substitute their values with the transformation. Yeah. So instead of ry, I'm substituting r sine theta. Okay, instead of rz h. Okay, and then this r is what? The Jacobian, the determinant of the Jacobian. Okay, so r dr d theta dh, or the right order, and this is my choice of limits of integration. So here z is going from, or h is going from minus this capital H by 2 to capital H by 2. Theta is going from 0 to 2 pi to cover the entire cylinder. If you have a semi-cylinder, you will have, say, 0 to pi. And here from 0 to capital R is my R coordinate. All right? Carry out this one, you should get this. Okay? And now this is the ZZ. Again, remembering that Z is, in this case, the axis of symmetry for this cylinder. Axis symmetry. And in total, if you calculate all the components of the inertia tensor, you will get this. Okay, so the x and the y, xx, yy, are the same here because of where is z. Okay, z is the special one. Okay, if you are getting a different cylinder oriented, say, about the x, then the x component will be this one, and the y and the z will be the same. Okay? Any questions? Okay. So what I meant here, just notice this is G, the red coordinate system that is nominally attached to the cylinder. But I had this comment, what if it's not attached? What if the cylinder is rotating about this z-axis? Or alternatively, what if we have a frame where the x and y are rotating and the cylinder is fixed? Because it doesn't matter what is the direction in space of x and y, as long as they are normal to z, which is parallel to the axis symmetry of the cylinder, it would be the same result. Okay, the same result. I am saying that because you have a similar case with your gyroscope, with the rotor rotating. Okay, so you don't even have to fix a frame to the rotor. You can work in frame 3 as long as you know that the rotor is rotating about the Z3 axis. Okay? It doesn't matter that your X and Y are not rigidly attached to the rotor in frame 3. Okay, so think about it. I just mentioned it. You will need to calculate inertia tensors, and frame 3 is a convenient choice for both the rotor and the frame of the gyroscope. All right? Does it make sense? Remember, the rotor is axisymmetrical about the Z3 axis. Okay? Okay, next shape is this torus, and in order to integrate its volume, I'm using another transformation of coordinates of the integration. It's a different one, and I made this transformation for you using the knowledge that we know already from kinematics, using rotation matrices, etc. Just, it is important that you notice that this torus is, so it's like a donut, right? And the axis here is ZG. This is my choice here for this example. Remember, this is ZG coming out of this donut, okay, like a candle. Okay? And in the frame of the gyroscope, you have two of these donuts, right? So if you're, say, working in frame 3, thank you. I nearly did that. Okay. So if this is the frame of the gyroscope and you have frame 3 attached to it, so let's say 3, and this is Z3, okay, attached to this one. And if you want to calculate I of the, say, gyroscope frame, in frame 3 about G is here. So you have two tori, this one and this one, okay? But then Z3 is going there. So only for this one, it will be just like we are doing today. And for this one here, don't forget to treat it in a different way, okay? So that, say, this axis comes out of it, okay? So don't forget to use the transformed inertia tensor accordingly to the orientation of the torus relative to the coordinate system. Do you understand what I'm saying? Yeah, so essentially be careful. This Z is the special axis here, all right? So how to define the transformation? What you see here is, let's say, two slices. This is slicing the donut as if you want to put cheese inside, okay, for a sandwich. And this is if you are cutting it quickly to share with a friend, okay? So I defined this red system of coordinates, xg, yg, zg, is as pictured here, okay, with the zg coming on top. You're hungry? I'm hungry too. Okay, now there are a few dimensions that I need to give to you. So R is this dimension until the centroid of this donut here. Okay, so until the center, this is R. And A is the cross-sectional radius, the small a. All right? So what I will be doing in the next slide is defining the position of an arbitrary point P, because then we would need to go from the center G to some arbitrary point P on the donut, so that we can explain what are Rx, G, Ryg, Rzg. Okay, so I'm trying to calculate Rxg, Ryg, Rzg, which along this red frame G, which is this vector here. Okay, so I need to use a general point P, and that would be some point in one of these cross sections. All right. So I'm using this blue frame, which is an auxiliary frame, and this one is such that the x of that blue frame, that I called it frame 1. So for frame 1, x1 is pointing towards the slice of interest, the cross section of interest, and this angle phi defines the slice. Yeah. So for phi equals 0, this is the slice. Phi equals, say, 45, this is the slice. And then I need to pick point P within the slice, within the cross section. Okay, so for this one, I'm using these r and theta coordinates, where theta is measured from x1, okay, x1, which is this one, and r is from the center. So O, point O, is the center of the section. Okay? So if you cut the donut in where it's black here, and then you open to look, this is what you see, this little circle. Its total radius is A. All right? And this small r and theta can locate a specific point for you. So I'm transitioning now from x, y, z to r, theta, and phi. All right? In your tutorial, you will work with another r, theta, and phi for spherical coordinates. Okay, but this is, let's say, torical coordinates. All right? And if you look at this calculation, I think it should make sense, right from the position vectors lecture. Okay, have a look. The result, does it make sense, what I'm doing here? Yeah, I'm summing vectors to get from G to P. So from G to O, that is R along the x1 axis, and then from O to P, which is this R cosine and R sine theta. And then I'm shifting from frame 1 to frame G, the red frame G. So this is the rotation matrix using this phi here. Okay, I'm sure if you don't get it right now, you'll get it. Like one more look. This is the results. So Rxg, Ryg, Rzg are the coordinates of this GP vector along the red frame G. Okay, these are the coordinates, and they come from this calculation. If you just carry it fully, this is the result. Okay, so this is essentially my transformation. And what I need to do now in order to integrate conveniently, because why am I using these coordinates? Because for theta, phi, and this little r, it is easy for me to choose the limits of the integration, right? What are the limits? This r is going from where to where? 0 to a, right? This theta from 0 to 2 pi, and this phi also from 0 to 2 pi to cover the entire donut. All right? So in order to be able to easily choose the limits of the integration, I'm working with these coordinates, and now in order to integrate with them, to substitute them instead of the, say, ry, rz, rx, etc. In order to substitute them, I need to also figure out what is the Jacobian of this transformation, right? So for the Jacobian, you construct this matrix, okay? And for this matrix, this is the Jacobian. Okay, so you would put this thing into the integrand, okay, right before the dr, d theta, d phi part. Okay, so in here, you can look at it geometrically or algebraically, either way. All right, I think algebraically it is easier. Okay, so now we need to construct the integral. I'm giving you the xx component. So xx is this. It has the ry squared plus rz squared. And I'm substituting the y and the z. I'm substituting here, y and z, okay, squared. And this part is the Jacobian, okay, rho can go out. And this is the total mass, okay. So overall, I didn't carry out the integration. I just took it from a table. But if you have extra time between assignments, you can do that. Okay. Otherwise, so remember this is the xx component. What would be xy? What would be yz? Zeros due to symmetry, because you have now, again, all the symmetry planes. So another one you want to perhaps check is the zz, moment of inertia. All right? So this is what you use. I'm referring back to what I stated at the beginning of this torus. This is the special one. These are equal to one another, but this is the special one because the z-axis is the one coming like a candle out of this donut. Okay? So make sure you don't forget to rotate or to change this matrix to your use when you have a kind of differently shaped donut relative to the red axis, okay, the body axis. And this is the last example using superposition here. You have a cuboid with two cylindrical holes. All right, cuboid with two cylindrical holes. And the transformation I'm using for each of these cylindrical holes, in order to easily specify the volume of these shapes, remember I'm starting all my vectors from G. Okay? So any arbitrary point along this cylinder number 2, I would need to describe this vector from G to a point P here. That's why I would need to have the limits of the integration correctly selected. And it is convenient to work with kind of r and theta, but let's say r2 and theta 2 for this cylinder, and they are not, if I would use the normal cylindrical coordinates, r would start from here, and yeah, you don't want that. So what I'm using is shifted cylindrical coordinates. Okay, you can look at the shift. Here are some convenient dimensions for the top view, what you see if you look here on the top. So just make sure you understand here. Theta starts from this axis, which is the x-axis here. Okay, so theta goes like that. Okay, and I have these different plus minuses. Have a look at that. And what I wanted to show here, for the entire shape, I'm going to calculate Ixy. Okay, so the inertia product, Ixy. And for the first time in this lecture, it's not going to be 0. Okay, Ixy is not 0, because essentially this Zx or Zy are not symmetry planes. It's not a good reason. I'll tell you why. Because sometimes you can have a shape that has no symmetry at all, and still you will have some choice of coordinates where the inertia products are still 0. So the inertia tensor is still diagonal. So it's not kind of if and only if. But in this case, you do have one symmetry plane, which is the xy plane. So if you slice this cuboid along the xy plane, whatever is on top and below is the same, right? The axis which is normal to this symmetry plane is z. That's why any inertia product with z participating in it will give you 0. So Izx or Izy will be 0, but not Ixy. Okay, so in this case, Ixy is not 0, and this is the calculation. So this thing here is the superposition idea that we've discussed, and here is each of the cylinders, and this 0 comes from the cuboid itself. So if you take the cuboid as a whole, we already saw that for it, the inertia products are 0, okay, in particular the xy inertia product. So we just need to correctly use the shifted cylindrical coordinates. But essentially, when you carry out this entire calculation, you are getting this value, okay? Remember to substitute it with another minus. So with another minus you have here in the matrix itself, minus ixy. So we just calculated ixy itself. Okay, it comes here with another minus. And the meaning of that, this kind of lack of symmetry that led to having this inertia product non-zero, what it physically means we will see a little bit later, but just as a, I don't know, little clue, it will, this will contribute to having some moment. If you say rotate this, if you look at this body and you start rotating it about x, yeah, rotating it about x, if you kind of place an axis here and start rotating it about x, this x-axis would start wobbling a little bit because it would feel moments about the y-axis, kind of. And vice versa. If you rotate it about y, it will kind of feel moments about x. Okay, so these moments would come from the Newton-Euler equation, h dot equals sum of moments, okay, where h is this I omega. I contains this inertia product. Okay, so think about it. I'll see you afternoon. Anyone who wants to swap labs, come down here and talk to one another. Okay, anyone who wants to come to my consultation, come to my office and I'll start it in 15 minutes. Thanks.
the top